Okay. So, so these are the two famous limits. There is another one. The interpretations are, I hope, clear in terms of the rate of change. Okay, so we're going to get to that later. At this point, we're gonna discuss the algebra of continuous functions, even though let's see how far we got with this. So so not only sine and cosine are continuous, but also the function behave continuously under our algebraic operations remain continuous. So the combined functions are still continuous. Okay, so the sum, difference, product, and quotient, or as long as they are defined, they're continuous. Okay, and then and that creates a huge library of functions that we can utilize and then use for computing limits. Even though the continuity of its own is quite important. So let me illustrate this once again. The something that we discussed, how they geometrically recognize these facts. So the summation is so two functions y. If they're continuous, they're the sum is also continuous. So you could say you have two functions, and hold on a second. Why is it here? Pins. Okay, where's black? Where's black? Where's one? Oh, here it is. Okay, okay, so two functions. So say one function. Well, so we remember we talked about that issue when we dealt with sequences. Okay, but this time it is actually simpler. So let's say this is one function, y equal f of x, and maybe this is another function, y equals g of x. Okay, so they're continuous and they plotted them as continuous. So now where is the difference? Can you point out the difference on the graph? The difference of the two functions? So if I pick a value here, say over here, I pick a value of x, then this is the value of g, so this is g of x, and this is f of x. Okay, for this particular, for each value of x, there are the two values. There will be give you simply the height of that location above the two locations above the x-axis. So where's the difference?
In the y value?
It is in the y value, but can you point it out? F of x minus g of x. Well, so it is this is the red one, and this is the green one, right? So the difference is simply the difference of the heights of these two bars. Okay, so here it is. Well, that color. I'll put black. No. Not this one. Okay, this is the difference. The difference is every time is the height. It's like you're moving through through a tunnel, let's say. Okay, a tunnel, and both the floor is uneven and the ceiling is uneven. But even though they're changing continuously. Okay, so and you might ask yourself, what about the actual total height of the tunnel? How is it changing? And for example, I mean, will there be at any point the danger of hitting your head? Okay, because it has changed abruptly. That would be discontinuity. And the answer is no. This will still be changing continuously. So if I build enough bars here like this, and then I could just arrange them elsewhere, I could put them like this. This is what the function would look like, right, roughly. This is the difference. And this function, if I now plot the top of it like this function will be continuous again. Okay, so that explains the difference, and it's similar of why the difference of continuous functions is continuous. The same for the sum of two continuous functions. And then something that we did previously with the product. Remember what we did with the product, two functions. What's the geometric meaning of the product of two quantities, of two lengths? The area. Okay, so in other words, you are thinking about a rectangle with a variable width and height separately. Okay, so like what I drew here. So both of them are changing, but then we are computing, in fact, we are computing the area. So this is what we're after. So if we were after the difference in the previous example, now we're after the area. So I guess you can still think about the kind of rectangle tunnel which you're facing now, and then the width of the tunnel is changing continuously and the height is changing continuously. Well, the whole area changing continuously. The width of not the width, but the area, the cross section of the tunnel, like this, will it be changing continuously? Okay, and the answer is once again, yeah, it will be changing continuously. Hold on a second. Yeah, like this. Okay. Okay, and then the quotients is slightly more complicated because you have to look at the angles, but otherwise also it has a geometric explanation. So these are the four. There is the statement there right at the top, why sine and cosine are continuous. They also has like a physics, if not physics, but kind of real life explanation why it's continuous. So it also can be explained in this manner. It is, imagine you have, remember what the sine is, we discussed it yesterday. It is so it is the unit circle, and then we have the angle, and this is my x, not the x-axis, but rather this. So this would be cosine x, and the other one is this one or that one. This is the sine of x. Okay, so so if you think about it, then we're talking about think about shadows. Okay, so you can think about say if it's cosine, imagine that there is a sun here. This is the sun, and it throws sunlight down. Okay, and then what we're seeing is the stick is moving continuously, and so x is changing continuously. X is the angle. Okay, and then the question is, will the shadow change continuously too? Yeah, and it is kind of believable that it's going to be continuous. In fact, you can do it slightly different. In how about the stick is fixed on the ground, but it is the sun that's moving. That is the actual reality that we're facing. So the sun is like this, and then so it throws some shadow, and then it slightly moves here. Then the next shadow will be this. Okay, so the question once again, if the sun is moving through the sky continuously, as we know, will the shadows also change continuously? Of course they're changing continuously. We can see how gradually they're changing. It never abrupt, with the exception obviously is like just at sunset, just at sunrise. Sometimes it really seems like it happens instantly. But it's still not. It still changes continuously. So these are good news. These are the how continuity is preserved on the many operations, with the only exception is the quotient, and you might divide by 0. So you remember, it's like denominator is continuously approaching 0. What does it do to the whole thing?
Zero.
No, the denominator is continuously approaching 0. What does it do to the...
Getting small.
The denominator is getting small, yes, but what about the whole thing?
It's getting larger.
Larger, and not, and the closer, as with this continuous process, it will continuously approach infinity. So that creates discontinuity, even though it continuously approaches infinity, not abruptly, but still it is counted as discontinuity. So so discontinuity, I want to give examples of discontinuities just for extra examples that are important just outside of mathematics as well. We could, for example, here's a discontinuous function for you, and that is grades. Grades from your score. So you have many assignments and they're average, and then you at every moment you have a score. At the end of the day you have a score computed. So we're looking at your total score, but then you have to compute letter grades. You have to assign the letter grades. For each score there is a letter grade. The rules are often very simple, as the ones that I follow is say if the score large is, let's say it is x, larger than or equal to 0.90, then grade, letter grade, say f of x is a. Okay, so that's the simplest one. And if it is x less than 0.90 but larger than or equal to 0.80, f of x is equal to b, like that. Okay, and so on. So if you try to plot it like this, then you will see immediately that you don't have too many options. If I put a, b, and c on the x-axis like this, on the y-axis, a, b, and c, and d, okay, then you realize what's happening here. It is quite problematic, but this is the piece of the graph, and then the next one piece of the graph. It is like a step function that changes every time we move through one of those cutoff points. So 0.90 is a cutoff point. Okay, so just looking at the graph, you can tell what the problem with cutoff points are. What is it? It is not continuous. So f is discontinuous at those points. Okay, and remember what it means. If we go back to continuity, it means that small error of the input, which is x, your score, will lead to possibly to a large or significant, not negligible error of the output. So it's if you look at the picture, it's also clear that there is no way to get around it. You see, because you cannot jump from A to B instantly without this discontinuity. So if there is nothing in between A and B, then it means that you are jumping. It means that there is a discontinuity, and that is the inevitable consequences. If you lose one decimal point, 1/1000th of your score, difference in your score might produce a letter grade difference. Okay, so and you can add A plus B minus, stuff like that. It will still be the same, have the same problem, because from the continuity of this is the we called it like a continuum of values of x between 0 and 1, maybe in percentages, doesn't matter, and then you have to translate it into two letters, and they are discrete. Okay, so continuous continuum, and these are discrete values. So that is inevitable, creates a need for discontinuity. So no matter, there's just no way around it. Another example, also kind of interesting, and that is taxes of all things. So I do not remember, well, I don't want to remember really, the actual numbers and that you pay, but so I made up numbers, and so this is what I made up. So less than 10,000, it is the zero rate, so you don't pay anything. If it is larger than 10,000, okay, but less than, so X is your income, or reported income, or taxable income, it doesn't matter. We are simplifying things significantly. So and if it is between 20 and 10,000 and 20,000, let's say it is 10% rate, and then let's have one more rate, 30,000 and 20,000. Yeah. So 20% rate. Okay. So you can see what any comments about this, about the relation. So these are x's and these are y's. The x's are your income, and the y is the tax rate. So this is, suppose this in some hypothetical location, this is the how the tax rates are computed. So any comments? Oh, look at it. What? Do you compare it to the last example? That's right. So it is discontinuity. So once again, there are cutoff points, and there are two of them. So there are two of them. There is nothing below zero. So so you can say that there is a cutoff point there. But at 10%, at 10,000, 20,000. Well, I'm sorry. I think I should just eliminate this. 20% if when you're anything above 20,000, let's say 20% hypothetically. So that way you have only two cutoff points, and they're discontinuous. At that point, you can easily plot the graph. It looks like what starts with 0, then it becomes, at 10,000 it becomes 10, and then at 20,000 it becomes 30, and continues on this way. Okay? 10, 20, and this is 10%, 20%. Okay, and so discontinuity is inevitable by the same reason. So, but that is why we're not actually in reality face discontinuity in real life, because these are in fact not tax rates, but these are marginal tax rates. You know what it means? Well, it's a fancy economics word, but it means that it applies to excess income above the previous bracket. So it's not really, so the 10% rate only applies to your income above 10,000. Okay? And similarly, 20% rate applies only to your income above 20,000. So this is still okay. So if I'm now trying to apply it as marginal application, so it's not that I pay 10% rate, 10% of x minus 10,000. So I have to subtract the non-taxable income 10,000 and then apply the rate. That's the marginal idea. So whatever how much I got past 10,000 is what being taxed at that rate. Okay? And then with 28, so it's slightly more complicated here because you have to first evaluate 10% rate on x minus 20,000. That will be the 20% rate will be applied to x minus 20,000. So the point, long story short, the rate are still kind of a discontinuous, but the actual amount will not. So if we look not at the tax rates, these are the rates, and that's this discontinuity, but look at actual tax liability. Okay, how much you pay, that function will be continuous. So let me demonstrate. So same idea. So these are rates. This is X income. I have still the same X income here, but now Y is the bill, the tax bill. Okay, so the same cutoff points at 10,000, 1,000, and 20,000. Okay, so the beginning is still the same. Once again, I'm not paying anything for the first 10,000. Okay, what happens then?
Goes up 10%.
But only on what's above 10,000. Okay, so so it's in other words, if I earn 10,000 and 11,000, how much do I pay? Subtract 10,000 first, I end up with 1,000, and then pay 10% of that, which means that it will be only $100. So in other words, it will grow gradually before it reaches the actual level of paying 10% of 20 will be, so well, let's just take to 20,000. When you are at 10,000, your liability is 0. When it's 20,000, how much do you pay? You pay 10% of 10,000, right? 10%, this is where we are. 10% of 10,000. Okay, so the excess is of 20,000 over 10,000 is 20, and so 10% of 10,000 is 1,000. So this is 1,000. Your liability, if you are paid 20,000, is 10,000. Okay, and how do you get there? Gradually, like this. Okay, and then the same thing happens, and then what happens then? Once again, as you pass 20,000, it's as if you split your income into 3 pieces. 10,000 that doesn't come into play. Then this is the stack of money. For 10,000, you take 10% of that, which is 1,000, and then what's left, that is higher bracket, and you pay 20% of that. So it will be growing faster than that. This is like 10% growth, and this will be, 20% growth, like this. Okay? So the discontinuity, how you get around discontinuity, and of the inevitability of discontinuity of rate from as you progress to the next bracket. But it is taken care of by design pretty much. Even though it is probably imaginable that sometime somewhere somebody set up progressive tax and then forgot to do this and forgot to put marginal as a part of the law, and then you realize, and then you are facing a pretty nasty thing if they forget about this, because suddenly you get a raise of 1,000 and then your tax grows by so much, then you are getting less than before. Okay, so but if you do it right, then this is what it looks like. Okay, so just an example of what can happen, what does happen, and discontinuity is sometimes hard to avoid, but as you can see, they primarily concentrated in human affairs. In the physical world, time is changing continuously. Nothing changes abruptly. If you don't want to go into like a modern physics, you just stick with classical physics. Then everything is moving gradually, and nothing. You don't teleport yourself or any object from one place to another. There is also no time machine to jump from one time to another. So if all of those things are ignored, possibilities of those things, then we do face everything pretty much continuous affairs. If you look at the modern physics, then some things come in pieces, such as say light. There are particles there. Okay, so it is kind of they are so small then we ignore it for the most part, but in a way it is like that step function. Okay, and every time we plot those functions, we actually facing the same story, that even though it is plotted, it's made of dots. If we zoom out sufficiently, it looks totally like a curve, a continuous curve. Okay, so continuity, discontinuity, algebra preserves continuity. The property of continuity is the definition is to be used. So let me just difference rule, product rule, and the quotient rule. And then there is the substitution rule, which is what we already talked about. Well, it has several forms. The substitution is it's about compositions. Meaning that so we just have looked at the 4 algebraic operations, and now this is the 5th algebraic operation on functions that we have to face. So let me just state it. Well, we already have seen it, so let me just have it say f of x squared, x goes to a. So this is the situation that we have faced previously, and at this point we don't want to go back to sequences anymore. We just know that the limit of we don't know yet what the limit of f is, but the square, this is the square, not the square, it's the square, and it is continuous. It is continuous in what sense? So we have y equal f of x. Remember how we decompose functions. So there are 2 variables. There are 3 variables in a sense. And then you have z is equal to y squared. So this is the decomposition. This is the decomposition with one function unknown and the other one is known. It is y squared. And what's so nice about y squared, it is a polynomial, and then we just say magic words in order to use that fact, which is y squared is continuous. And everywhere, at every point. So that is why the computation becomes, it gets simplified. Not simplified, but rather we are bringing a limit inside of the inside the parentheses, like this. Okay, so, and we take the square out. Because the square is a continuous function, it does not affect the limit. It is what you would think it should be. So this is the answer. Limit f of x squared. Okay, so in the first line we had, if we read it carefully, we start with function f, then it is squared, and then we take the limit. Okay, so that's what it is. Turns out we can interchange the order operations, and now as you can see, f is followed by the limit, and then it is squared. But what literally happens is this is a substitution. Substitution. So the limit to be computed is instead computed the limit of the function on the inside, f, and then the result of that is substituted into the new function, into the function, the outer function, which happens to be continuous. Okay, so that's how it works. And that function is replaced with, whenever necessary, is replaced with the square root. sine, cosine, any polynomial. So and then every time it works out in the exact same manner. So let me substitution rule. Let me write it. So if say g of y is continuous at L. Hold on a second. That is the second part of the statement. So we have two functions f and g. So f is still the function on the outside and g is on the inside. So first, the limit of y equal f of x at x as x goes to a exists and equal to L is equal to L first, and second is where we'll look at the second function comes in, and now it is now evaluated at L. So g, let's say z equal g of y is continuous at y equal L. So that is the composition. So so it's still possible that x is undefined at a, but the limit exists. Okay, so it might look like this. This is a, and this is y equal f of x, and this is y, and this is x. And then what happens is we are doing composition. So this is function g now is defined on y's. Okay, and this is L. So the function f is well behaved. The limit exists equal to a, equal at a is equal to L. Okay, and now we're looking at the function a function g that is is continuous to begin with. So it's continuous at that point L. That is I am referring to the same point L over here as over there. Okay, so it's the same function as it is. The input of the second function is the output of the first. Okay, so this is z equal g of y. Okay, and this is z. So they're kind of composed that's how compositions work. The vertical axis, which is the output of the first function, then it travels all the way like this, and it becomes the input of the second function. Okay, so what we're talking about then is g of f of x. Okay, so another notation is for g circle f of x. Remember this notation with a circle for compositions on the right? Does it look familiar? Yeah. Okay, so it's once again this substitution. It's just different notation. It's if the first line is how we compute it, and the second line is what we name it. So that circle is just like an operation on functions. Just like addition, you can add functions, you can compose functions. So that's the meaning of that notation. So we're looking at this function, and then what I don't have the conclusion yet, but let me draw the function decomposition. So well, how about h? So h, what's the input of h of the composition? X, y, or z? No, look at on the right.
Z, right?
No, that's the output.
Oh.
The z is the output. As you go through two steps, so you get from step number one, you start with x, right, like this. You start with here, then you go on, get a y, and that you take that y over here, and you get your z over there. Okay, so that's a double two-step procedure, two consecutive functions. And the result is the intermediate value is dropped. It is the initial value is x, as you can see. So if you just follow those arrows that I have, you start with on the x-axis and you end up on the z-axis. So h is on the x-axis and might look like this. And this is now what we're talking about. This is a, and this is whatever that is. Okay, so the conclusion is, however, that the limit limit does exist. So this is the setup again, the setup of our theorem, and now the conclusion is very simple, that the limit is to be computed, a limit of g of f of x as x approaches a is g of L. Okay, so this g of L is what we have found here, the substitution. It looks more harder, I suppose, than the reality. Say I'm talking about this limit of the square root of x squared plus 1 as x approaches 1. Okay, so if we look at it carefully, first of all, let's suppose we are just randomly given this problem, then we have to analyze the function first before we get to the limit. And remember, we don't have too many things to apply when we're computing limits. We have four rules, algebraic rules for the four algebraic operations, the substitution rule, and then we have some of the functions that we already know for a fact are continuous. Okay, the continuous functions are polynomials, rational functions away from the holes in the domain, and sine, cosine. So that's so far the only functions that we know. So that is not one of those continuous functions to begin with. Okay, so we discard that. Then we tried the four operations. We tried the four operations, and we realized that none of them apply. Why? Because what is the last operation of this function? The square root is the last operation, which means that there is no square root rule of limits. The last operation is the square root, and it is applied to the whole thing x squared plus 1, which means simply that you have two consecutive operations, which means that there is really no other, none of those four rules will apply. So none of the four rules apply. Okay, but fortunately, once you recognize it as the composition, then you know that then the conclusion is decompose, meaning decompose as represented as a composition. So we take my function, and x squared plus 1 is equal to g of f of x, and I can just mark. We know that the square root is the last operation. Let me mark it with red. And that is the function that applies, comes into play last. Okay, so then what I say here is I say let call this y, and that will explain to me what g is. So what is g?
Square root of y.
So square root of y, that's right, square root of y. In the meantime, f of x is, which is y, is equal to x squared plus 1. Okay? So that is the decomposition, a very important step that appears a lot, not just in limits. And then we look at these functions and ask ourselves, what do we know about these functions? We know that we're going to use the substitution rule, so the continuity becomes an issue, and which fortunately both of them are. This is a polynomial, so you have to use some reference words in order to justify your steps. So here it is. If you want to conclude that the function is continuous, and we'll always do if we compute limits, you have to say what kind of function it is to make sure that it is. Okay. So x squared plus 1 is continuous as a polynomial. Okay, so it is a polynomial, so it's continuous, so we have no trouble computing its limit. The second one is slightly more complicated, and so that's why you have to okay, now I realize I got this ahead of myself, but so we just have to accept this on faith. We didn't have demonstrated that this function is actually continuous. I could have picked sine and cosine, at least we had discussion of that. So let's assume that g of y is continuous. We certainly will demonstrate that eventually. And then if that's the case, then a substitution rule applies. The formula is right there, so all the conditions in green here are verified. The limit of L, well, first of all, where's my L? Well, the function is continuous, by the way, but it is, you have to be careful where the function is defined in the first place. It's undefined at 0, at less than 0. And as far as 0 is concerned, that's where it has only a one-sided limit, because its domain is 0 inclusive to infinity, which means that at 0 x cannot approach from the left, which means that you cannot possibly have a two-sided limit. But as long as y is positive, we have a continuous function. So then to be able to apply our theorem, we have to step 2, we have to demonstrate continuity at what value? Well, so continuity at what value? So let's find L first. And L is the limit of f of x approaching a, which is x approaching 1 of x squared plus 1. We evaluated by substitution again because the function is continuous, as we know. So we simply have 1 squared plus 1, where it is 2. So that's my L. As you can see, we split two functions into the one function into two and deal with them separately. We're looking at L, so the function on the inside, function f, is continuous. We took its limit. We found it because it's continuous. There we have our value of L, which means that this is the value, the only value for y that we care about. At this point, we don't really care anything about the rest of the values. So we just state, without proof for now, that g of y equal to square root of y is continuous at x equal L, which is 2. Okay? Once we plot that function, it certainly will be believable. And then we apply the substitution rule, and the limit of our function of the whole thing becomes simply it will be square root of 2. Okay, so that 2 is substituted into g. So that's my square root over here, and then I substitute the value that we found, the value of L, into inside of that function. Substitute literally, so we just evaluate the function at that particular value of x. That's it, and then that's the end of it. Okay, so that's just an example of application of the substitution rule. It looks longer than it actually deserves, because at the end, if you look at it, the whole function is continuous, and you could have, if you just think about all the in between is just the beginning and the end. All in between is just justification. Justification why we're allowed to do what we do. But in reality, it is look at it. It's simply, instead of saying that x is approaching 1, we're saying let x be equal to 1, and that is the last line, right? 1 squared, square root of 1 squared plus 1. Okay, so. And at the same time, we're proving that the whole function is continuous as well at that point. So that is the rule. Let me rewrite this rule in a slightly different way, so that it's slightly more compact, but the conditions still apply. So this is what it looks like. So it's a limit. So without using circles, but rather using instead large parentheses. Okay, so limit is applied to this composition, f inserted inside of g, and then I could just pull g out and pull limit in. So that's another way to put it. Okay, the substitution rule. So half of the time, just saying that the functions are continuous will do the trick, and you can compute things that way. So so imagine, let me tweak this a little bit. So you can imagine what happens if I replace the square root with sine. Nothing changes whatsoever because sine is a continuous function. Okay, I can replace it with cosine. I can replace it with any kind of power. As long as I know that the function is continuous, the process is exactly the same. There is no change whatsoever. So it is these parts. As long as these parts are known, the functions are involved are continuous. Then all you have to do is just to substitute. I guess most, in my experience, this part is actually more complicated. This decomposition. That is something that just understanding compositions and being able to compose and decompose functions is a bigger challenge than actually limits themselves. Okay, so we'll look into that a little bit more. Let's so there's one more operation on functions, and that is the inverse. Remember what that is? The inverse. It's like reverse, only better. So like addition, how to reverse the effect of a function. That's what the inverse does. So you add 3, subtract 3, multiply by 2, divide by 2, square the number. How do you undo it? Square root. Okay, sine, arc sine. Okay, so pairs, and they go both ways. So make no mistake here; they go both ways. So how do I undo subtraction by subtracting 3? The answer is add 3. Okay, and the same is to undo the square root, I square, roughly. Okay, so so the common pairs of inverses. Okay, so I guess the most typical example is this, but it's also challenging because the function is actually does not have the inverse, if you might remember. So let me plot it. So if I have the square, y equals x squared. Okay, so this is y, this is x, and this is, so we convert x's into y's, and then what's supposed to happen is I'm supposed to have a function that would convert y's into x's. Unfortunately, it's really uncomplicated. You just reverse the arrow, reverse the process. So you can actually recycle the same graph. What happens is the dependent variable becomes independent and vice versa. So you don't even have to do anything with this graph. You can just look at it and just in your mind just decide, well, I'm not going to think of x as independent variable anymore, but it's going to be the dependent variable, and same for y. Okay, so vice versa for y. So it means that we will be going, rather than as we normally do, we go vertically like this, and then horizontally. And we decide, well, let's do the opposite. We are going from y to x. Okay, so then let me write out these pairs. If I want 2, 3, 4, if I want to do it algebraically, I have 1. I have x plus 3. The inverse is y is equal to x plus 3 is my original function, and then I invert it. What do I have? It is x equal y minus 3. It's the same equation, right? Same equation. We just decide that we flip the independent variables. So y is equal to 2x. The inverse is what?
Y over 2 equals x.
Yes, y over 2 equal x, that's right. And this one is tricky because x squared, and the inverse is x equals square root of y. The trouble is that the reversal is not unambiguous. If look at the red arrow, you see the problem? So the plan is that for computing the functions is go from your input, which is right here. We're looking at the inverse function, right? So my input is y, okay, and then from that I'm supposed to go horizontally until I hit the graph of the function, from which point, as that arrow shows, I find the corresponding value of x on the x-axis. Sounds good, but what's the problem? Look carefully at this point. So once again, let me repeat it. From that point, you're supposed to go horizontally until you hit the graph. You see the problem? No, you don't see the problem. You don't see any. You don't see a problem. I said horizontally. I didn't say go to the right. You could just as well can go to the left.
Because it's not a function that way.
Exactly. So what we have built, if we take it for granted, what we see here, the result is not going to be a function. Indeed, that's exactly the problem. So, and you can see it because that horizontal line will have two intersections with the graph. In fact, you might remember what it's called. It's called the horizontal line test. Do you remember test for what? So first of all, the test is whether or not the horizontal line, well, you do remember the vertical line test.
Yes.
Right, so it's the vertical line has to have at most one intersection with the graph. Okay, but that's what happens. If you flip x and y, the vertical becomes horizontal and vice versa. And so the same horizontal vertical line test becomes horizontal line test. So in other words, we're testing exactly for that. We're testing for the inverse function to be function. And we discover that it's not because as you can see, this one is technically fails the vertical line test. Okay, and that it manifests itself on the graph of the original function as the failure to pass the horizontal line test because, as you can see, there are two intersections. Okay, and that is the ambiguity. If you're looking at a square root of 1, square root of 1 could be 1 or negative 1 in that sense. Okay, so if I square 1, it's 1. If I square negative 1, it's also 1. So there you go. It is not unambiguous, and that we cannot have that if we're talking about functions. So the test, it is test for invertibility, also known as one-to-one. Invertibility meaning does it or does not have the inverse. So x squared does not have the inverse as it's stated, okay, because there are two square roots of every positive number, and it fails the horizontal line test. Okay, so if you're not sure, that just flip and look at the graph. The graph will look like this, right? And that certainly is not the graph of a function. Okay, so if you want to put y here and x there for convenience, then that's not the graph of a function. So okay, so that's the horizontal line test is a test for invertibility. So what do we do? How do we make sense of this? If you remember. I mean, we do know that square root does make sense, and we want to have the inverse function here, so we want to introduce, in fact, that's the meaning of, what is the meaning of the square root? It is exactly it. It is the inverse of the square function. Okay, so we want to have it, but we can't have it just like that, so we have to tweak it. So remember what you do with this? So no inverse and we really want it. So the function is not one-to-one. In other words, the two inputs provide the same, two different inputs might provide the same output here, like this, right? So I square -1, I square 1, give me the same result. That is not one-to-one. Okay, so how do we make it one-to-one? So make the function one-to-one. How? Just throw half of it. There's really not much we can do, and not much else we can do. We throw half out and we keep this. As you can see, it passes the horizontal line test. So the square root makes sense as long as the x's and y's are non-negative. Okay, that's pretty much the whole thing. Okay, so that was a review. And then now the good news is that's fairly simple, and it is. Let's say to the theorem. So the inverse of a continuous function is continuous. So if y equal f of x is continuous at x equal a, and naturally we require that f is one-to-one, then x equal f inverse, that is, remember this notation, f inverse with a -1 is continuous. And the trick is to tell exactly what that point is. Can you tell at what point the inverse function is continuous? It's got to be y. That's why I put y there. So there would be we wouldn't try to think about continuity of inverse at a, because a is the value of x. And you remember those x's and y's might have nothing to do with each other. They could have, one is in time, the other in space, or these are pounds, these are pounds, these are miles. So we don't want to mix them up. So the inverse function will take, so if the original function took, say, seconds into meters, this should take meters into seconds, and the y should be then meters, not seconds. Okay, so what value of y is the only suspect? No, it's no. Look at the graph again. Y equal. Okay, so this is my function y equal f of x. And we are claiming the continuity, so the function is already one-to-one, not to worry. So this is, then we are here. This is where that cross is. That is where we claim continuity of our function. Then, before we proceed to that, think about the graph of the inverse function has the same exact graph, except it's kind of flipped. But you can draw the graph on a piece of paper, and then you flip it. Or if it was continuous on this side, you flip it, well, it's still continuous, right? So it's because you flip the piece of paper, that curve that is drawn on it is not going to break, right? So, okay, so that is good news. The continuity is preserved because there is nothing is happening. The function, there are two functions, but they represented the same relation between x and y. And so if that relation is given by a continuous curve, then it means that both of the functions are continuous. Okay, so that's good news. But if we want a precise statement, here we have to just point out the value of the function of the inverse function where the function is continuous, because we do continuity one point at a time. So this is x, this is y. This is the only suspect. So this is a where the original function is continuous, the value of x. This is the value of y, and that is the only one point that we might worry about. So what is the value? What is this? The green dot, what's the value? F of a, yes. Okay, so if you just want to be careful, and as I said, do continuity one point at a time. It's like one big curve, and then you go one point verify every single, like I don't know, pipeline, and you verify every single inch. Where is there a break? Is there a break? And you keep walking like that, or it's maybe a railroad. So it is the sometimes we just say the whole function is continuous if it is continuous at every point, but it is frequently the case that there are gaps somewhere else, and so we don't want to jump to that conclusion. Okay, so that's good news, and that what does it tell you? It tells us that the square root is continuous to begin with, even though not everywhere. So because we had to cut the domain in half, so it is only defined on positive values of y. At 0, it has a one-sided limit. Arc sine is continuous. Arc cosine too. Because sine is continuous, that arc sine is continuous, right? So that works out. All kinds of roots are continuous. So we know that the cube is a polynomial, it's continuous, so its inverse is cubic root. Just like with the square root, we have a cubic root, it's also continuous. So we have a bunch of roots that are also continuous. And then there is this function that we sort of skipped, but sooner or later we have to face it, and that is the exponential function. We actually saw a little bit of that recently when we talked about sequences. F of x is equal to a to the x. Okay, so that's a big topic, and I just hope you have enough in your background to remember basic rules of handling exponential functions. Of handling meaning that you might remember algebraic operations. Remember algebraic operations with exponential functions, like what is this equal to? So all of that will certainly, yeah, if you remember. No, it's actually a product of the two. The formulas are hard to remember if you don't remember what's behind it. But remember that just like multiplication is a repeated addition, exponentiation is a repeated multiplication. Okay, so all you do is just doing factoring, just like I don't know. It is like what is it? Yeah. So let me see. X plus y times b is equal to bx plus by. Okay, so that's a rule. That's the what is the distributive rule of addition. So you distribute b over x and over addition. So multiplication and distribute over addition. But then you do pretty much the similar thing with distributing multiplication over exponentiation over multiplication. So where you see it is yeah. So imagine that ax, if x is an integer, then you just multiply a by itself x times. Okay, and then a to the y, a by itself y times. Okay, so if you have ax times ay, you have a bunch of a's repeated, first x times and then y times, and altogether it's x plus y times. Okay, so that's where the rules come from. They're just kind of filling in the blanks, but the ideas come from dealing with integer, or rather natural numbers for the exponents. So this is once again xy natural. So it's a starting point, and then you have to, the rules are like this. You see how I pretty much, if we ignore this for now, this is how we explain this formula. It is a repeated multiplication. Okay, so you multiply either x plus y times to begin with, or you multiply x times and then y times. Altogether, it's x plus y. Okay, so you're just counting the number of how many times a has appeared there. Okay, so that's same with the rest of the rules. Okay, that's certainly not the end of the time. The end of it, because there are fractional x's and then there are natural x's. So all of that really needs to be taken care of. But the end result is really, once you get through those kind of hard, difficult things, this is the graph of the function. If a is positive, y equal a to the x. That's what it looks like. It doesn't look like any of the other functions. It doesn't look like polynomials. It doesn't look like trig functions or even rational functions. And so we will talk about that a little bit next time. But you try to review these, because that comes up all the time. And the models are, remember the bank account that we talked about. It is growth of population decay, radioactive decay, radiocarbon dating of artifacts. That all is based on the exponential functions. Okay, so I'll see you tomorrow then.